Hello everyone, my name is Zhangyao, a graduate student from Beihang University. Today, I am delighted to present our work titled, Interaction-Aware Shared Scene Synthesis for VR Telepresence. This research was conducted in collaboration with Qixiang Ma, Runze, Xiao and Lili Wang. What are the essential elements of VR Telepresence? First and foremost is a shared virtual scene. This is the foundation of remote interaction, allowing users in different physical locations to feel as though they share the same space. Second, interactivity and safety are crucial. Interactivity ensures natural and fluid engagement, while safety guarantees that users can navigate their physical environments without harm. These elements have broad applications, such as in VR, and are remote meetings to break down geographical barriers for efficient collaboration, in remote education, and in collaborative tasks where team members work together to boost productivity. In the realm of VR telepresence, finding a reasonable shared area among the heterogeneous physical spaces of remote users is highly critical. Existing methods include area-based matching, interaction target-based matching, and clustering based on relevant objects and layout relationships. These methods address different VR telepresence scenarios, and have laid a solid foundation for subsequent research. The core challenge of remote interaction is synthesizing virtual scenes that feature diverse styles while meeting specific interaction needs. Previous methods, whether based on layout rules or neural networks, have notable limitations. They often generate scenes lacking diversity and ignore user behaviors in the physical space, making it difficult to meet complex, real-world demands. Conversely, emerging large language model (LLM) agents show significant promise. They can generate virtual scenes in diverse styles and accurately understand various user requirements, offering a novel direction for virtual scene synthesis. Our method focuses on interaction-aware shared scene synthesis. Users can easily describe their needs regarding collaborative tasks, scene types, and desired virtual experiences. By precisely aligning the physical rooms of the users, we generate a suitable scene layout with diverse styles and rich virtual objects within the aligned area. We pioneer the first framework that deeply integrates user requirements, physical layouts, and the virtual scene synthesis process for VR telepresence, providing a brand new solution for remote interaction. Our workflow consists of three main parts. First, the user initiates a remote interaction request and provides a description of the intended interaction. Second, taking the user's description and the pre-uploaded 3D semantic segmentation data of their local space as inputs, we perform a local space alignment to obtain the shared area for remote interaction. Finally, we generate a virtual scene within this shared area that fulfills the user's requirements. The complete pipeline is divided into three modules, corresponding to Section 3 of our paper. First, we introduce the interaction-aware template, which represents the necessary structure in the virtual space to facilitate the user's desired interactions. We utilize affordance as a metric to evaluate the suitability of a specific location for a particular interaction. We employ an LLM planner to process the inputs and generate this IoT. As shown in the figure, the generated relevant data is transmitted and parsed in JSON format. In the second part, we generate an affordance field based on affordance analysis and transform it into a probability distribution using an anisotropic Gaussian function. Furthermore, we design a scoring function to calculate the matching degree between the affordance field and the IoT. Serving as a bridge connecting different user spaces, the IoT is thereby mapped into a local shared area that meets the interaction requirements. In the third step, we generate the final virtual scene based on the merged affordance fields. We categorize virtual objects into three distinct types, based on their level of participation in the interaction. As can be seen from the figure, the template object serves as the core structure necessary for the expected interaction. The additional objects are reasonably attached to the template object, meeting the user's needs and enriching the interaction activities. The decorations are used to enhance the immersion of the scene. Subsequently, we design an optimization function to maximize the physical space coverage by virtual objects while satisfying layout constraints, thereby achieving a shared scene layout with high virtual physical consistency. We conducted experiments on both synthetic and scanned scene datasets, comparing our approach against three existing methods. The evaluation metrics include free space ratio, affordance consistency, 3D intersection over union, and layout suitability. Here are some examples of the shared scenes generated by our method. Compared to the baseline methods, our approach more effectively captures the key interaction structures required by users and matches a more appropriate local shared space. In application scenarios, where sitting is the primary interaction behavior, our method achieves the best performance across all 4 metrics. In scenarios dominated by walking interactions, our method is slightly outperformed by the area-centric method in terms of free space ratio, but still achieves the best results in the other 3 metrics. Finally, we conducted a user study. 14 participants completed the experimental tasks and rated 2 specific questions. The experimental results demonstrate that our method yielded a significant improvement in the user's subjective perception of interaction fitness and sense of safety over the state-of-the-art baseline methods. In conclusion, we propose an interaction-aware shared virtual scene synthesis pipeline. Our main contributions include the definition of the interaction-aware template and its construction methodology using an LLM planner to understand users' physical space layouts and interaction demands, an IoT-based affordance field alignment method for generating the merged affordance fields of the remote users, and an LLM-based shared scene synthesis method based on the merged affordance field. However, our work still has some limitations. First, the size of the shared scene is restricted by the user's local spaces. Second, because we retrieve objects from a predefined asset library, the visual similarity between virtual and real-world objects remains limited. Third, we have not yet experimented with scenarios involving 3 or more users. Lastly, the user study did not deeply explore the time and success rate of users completing specific remote tasks. In the future, we plan to explore partitioning the templates for multi-user settings, extending to more types of affordances, and incorporating other avatar methods to support large-scale, multi-user shared virtual spaces. We also aim to integrate 3D generative methods to enable better alignment with the local environment, thereby improving the visual coherence between virtual and physical objects. Further experiments will be conducted to evaluate these advancements. Thank you for your listening.